Alright everybody, welcome to the 5-8 notes. This is going to be polynomial models in the real world. So already this year we've looked at different kind of models. We've done linear and quadratic regressions, so we're going to look at those again, and then we're going to add cubic and quartic models also. So this is a lot of calculator and then some understanding of what we're doing, but we really need you to understand your calculator and to have your calculator. So polynomial functions can be degree 0, they can be linear, they can be quadratic, cubic, and so on. We've talked about that. The essential understanding here is that we can use polynomial functions to model all sorts of real-world situations. When we do that, we're going to use a graphing calculator like we said, and then we're going to enter the data into list 1 and list 2, and we're going to use 3 different regressions. Linear regression we've used before, quadratic regression we've used before, and then cubic regression we're going to use now. Okay, so it'll be a little bit different in a TI and a little bit than a Casio. So I'm not going to do TI and Casio stuff on the notes, but since we've done this before, it should be pretty self-explanatory. Make sure you bring your calculator to class, and I'll show you in class if you're having any trouble as we go. But it's the same stuff that we've done before with regression. So the point principle, what this is right here, is for any set of n plus 1 points in the coordinate plane that pass the vertical line test, there's a unique polynomial of degree at most n that fits the point. So if we have 2 points, then we would use a line. If we have 3 points, a parabola, so quadratic. 4 points, then we're going to use a cubic, and so on. So however many points, we're going to go 1 less, and it's going to be that degree of a function. So take these points right here that we're given, and we're actually not going to, they're going to use a matrix here, and we're not going to do that. Okay. What we are going to do is we're going to use this. We're going to use a cubic regression. Okay, so we should be able to put those points from up above into our calculator, and we should be able to get right here, and because we have 4, we're going to use cubic regression, and then we should get these numbers right here, and it tells you where to plug them in, and then you just write out that function, so your answer should be this. Go ahead and try that on your calculator with these points that are given. Plug those into your calculator and see what you get for the got it number 1. Okay, go ahead and try that now. Pause the video and try that now. All right, you've unpaused. Hopefully in your calculator you got y equals 1.667x cubed plus 1.3 times 10 to the negative 12 x squared. That just means that's a huge decimal 0. This is scientific notation here to make it shorter. Minus 4.667x plus 5. Okay, and that went a little bit off right there. So that's what you should get. If that x squared, if that quadratic term is confusing to you, we'll talk about that in class. That's just a 0.000000013 x squared. Okay, and your calculator would have given it to you in scientific notation. Okay. Let's take a look here at problem number 2. The chart shows how much milk Wisconsin dairy farms produced in 55, 80, and 2005. What linear model, so they tell us in the question, linear model best fits this data. Use the model to estimate the milk production in 2000. This is just a linear regression. We've done this a lot. You did it Algebra 1, some of you in AFDA. We've done it in this class. So then you need to have this in your calculator so we get that line. And then for the got it number 2, we're going to use the same model and predict how much milk is going to be produced or was produced in 1995. Go ahead and do that. How much milk was produced in 1995? Keeping in mind that this is in billions of pounds. Billions of pounds. So how much milk in 1995? Go ahead and pause the video and try that. All right, you've unpaused. Hopefully you got 22.56 billion pounds. Okay. Again, if you're having trouble with your calculator, I would suggest go back and watch some of the old notes on regressions and see if that helps you. Make sure you bring your calculator with you to class, and we can answer some of those questions in class. Here, the graph shows the quadratic model for the milk production in problem 2. Okay, the quadratic model fits the data points exactly because of the n plus 1 point principle. Given that both models are good fits, which seems more likely to represent milk production over time? Okay. The linear model constantly rises, The quadratic model has a down and down end behavior. It shows slowing growth, a turning point, and then a decline, eventually to 0 and negative values. Despite when we looked at this, we looked at the r squared value up top here. You know, this number right here that shows us how strong of the fit it is. So despite the r squared value of 1 for the quadratic model, the linear model is more likely to represent milk production over time since it shows a continuing increase. This is just looking at a set of information and trying to figure out what makes the most sense. I mean, if this is milk production, it's not like we're going to stop producing milk and then we're going to end up producing negative milk. That doesn't make any sense. The population of Earth is growing. It would make sense that the production of milk would then grow. Take a look at Got It 3. If 4 data points were given, would a cubic function be the best model for the data, and explain your answer? So go ahead and pause the video right now and think about that. A cubic function, would a cubic function for this data, say we gave you 4 points, would a cubic function, so something like this, would that make sense for this data? Try and write just a couple sentences down, a sentence or phrase, something to explain your answer. Pause the video here and do that. All right, so here's what I said. I said that the cubic model would fit the data better than the linear model because of the point principle. Both models have down and up end behavior, so they both make sense as far as that goes, and they both have increasing growth. The cubic model would show some signs of a slowing growth followed by a rapid increase. That could have to do with changes in technology or industry or things like that. So both of them are pretty good. The cubic model would fit the data better, though, because of the point principle. You might not have exactly what I put, but something along the lines of the cubic model would be better, but they're both good models. When deciding whether or not a model is reliable, it's important to consider the source of the data. Okay, data generated by law of physics or geometric formula will have a mathematical model that fits the data. With other data, such as like sales, things like that, the data is going to be an approximate or within or close to. So you have to be careful. Using a model to predict the y value outside the domain, okay, and we talked about this in Algebra 1 also. If we're going to use a model to predict data outside, it's called extrapolation. If we use data to predict a model on the inside of a set, that's called interpolation. Interpolation usually yields more reliable estimates. Extrapolation becomes less reliable as you move further away the data because you just don't know. Okay, and that's more application real world stuff. So how do we use them? Okay, so the table shows the annual consumption of cheese per person in the United States for the years 1910 to 2001. So we use a cubic regression, model the data with a cubic function, graph the function with a scatter plot of the data. So here's the scatter plot and all that. Since r squared is close to 1, it's a good fit, and the cubic model is approximately this. Okay, so this is just all calculator stuff so far. Now, use the model to estimate cheese consumption for 1980, 2000, and 2012. In which estimate do you have the most confidence? Right? So which of those estimates would you have the most confidence? So when we look at this, 1980 is within the data. 2000 is is still also within the data. 2012 is outside the data. Okay? We can use our calculator to do all of those and do a y calculation. That's not hard. And so we get 12.6, 29.4, and 46.2. We can be really confident in the data from 1980 and 2000 because they are inside. They are interpolations. The extrapolation data for 2012, it's an estimate because the cubic model starts increasing so fast. Like we just have to think logically. It's not going to continue on this, or there's going to be so much cheese like that. It's going to be like Cloudy with a Chance of Meatballs going really, really bad. Just an interesting reference, but so data outside, extrapolation, the data is not as reliable. Okay, let's take a look here at number 4. Use linear regression to find a linear model for the same cheese data. So same data, okay, that you've already put in, but instead of using a cubic function, a cubic regression, go ahead and use a linear regression. Graph that with a scatter plot, and then use that model to do the same estimates. And which of these estimates do you have the most confidence, least confidence, and explain. So same thing now, just with a linear regression. Go ahead and pause the video and do that now. Okay, so here's what I got. I got y equals 0.26986. You could stop anytime. 7411x. minus 3.919692952. Again, you could have rounded at any point. That's what I got for my equation. In 1980, I got 17.7 pounds. In 2000, I got 23.07, and in 2012, 26.31 pounds. And again, the same thing applies here. The data that I'm most confident in, okay, we're most confident in 1980 and 2000 because they are inside the data we have. I'm going to be less confident in 2012 because it's outside the data. Okay, that's an extrapolation, so I'm less confident about that. All right, that's it. It's a lot of calculator stuff. Make sure you bring your calculators next time. We'll make sure everybody knows how to use them, knows what they're doing, and can do this kind of stuff with the greatest of ease. All right, see you next time. Bye.